Thank you very much, Laure, for the introduction. So, my name is Jean Christophe Calvet. First of all, I would like to acknowledge the contribution of my co-authors, Yann Baer, Bertrand Bonan, Timothée Corchia, Oscar Rasmussen, Pierre van der Becken, and Jasmine Dural. So, my presentation will not be entirely dedicated to fires. There will be some machine learning and also a more general presentation of what we can do to monitor droughts by assimilating observations. So, to monitor drought, of course, you need to monitor soil moisture, but this slide shows that you also need to monitor vegetation, because vegetation provides biological control of evapotranspiration and carbon fluxes. So an example of that is this figure on the right. This figure is extracted from a simulation for a grid cell located close to Toulouse in France. So on the top you can see what we call the leaf area index, which is a quantity which is expressed in square meters of leaves per square meters of soil. And at the bottom you can see soil moisture at a depth of about one meter. And actually it's a comparison between two experiments. In the experiment in blue, we use a climatological seasonal variation of LAI. So this is for several years, from 2001 to 2004. This includes 2003, which was a very dry year in France. And in orange, you can see what happens when we simulate interactive vegetation with an interannual variability of leaf area index. And you can see the consequence of assuming that there is no interannual variability in LAI on the simulated root zone soil moisture. And you can see that the difference between the two experiments can be very large. And if, for example, you want to calculate a magnitude of drought using these soil moisture simulations, you will get different results if you have an interactive LAI or not. So this demonstrates that LAI has an interannual variability. And of course, as any land surface variable, you can have uncertainties in the description of LAI. And these uncertainties will propagate to the water, energy, and carbon budgets. So the question is, can we constrain these simulations by integrating into the model satellite observations which are sensitive to LAI? And this would help constrain both LAI and soil moisture. So we have a number of LAI products derived from satellites. So in Europe, we have what we call the Copernicus Land Monitoring Service, which produces new real-time values of LAI at a global scale based on Sentinel-3. And we also have EUMETSAT products of LAI derived from Meteosat and METOP. In addition, we also have microwave observations which can be sensitive to vegetation, and also a new variety of observation which is called solar-induced fluorescence. And this can be observed by hyperspectral instruments dedicated to atmospheric composition. So in this way you can observe the emission of vegetation related to the excess of energy of photosynthesis. Yeah. So this is an example of the relationship between LAI and soil moisture. So these are observations actually we made on our Météo France campus in Toulouse. So we have there an ICOS station. ICOS is a European network for fluxes. So what you can see here is for year 2022, which was very, very dry in France, we had a very severe drought, never seen before, including in Toulouse. So this is just to illustrate that in years where at the end of the winter you have very warm, very sunny conditions, and this is more and more the case in France, you still have water. So SWI is soil wetness index in the soil, the root zone soil moisture if you like. You still have water in the soil, and the conditions are perfect for vegetation to develop. So this is LAI. We have measurements of LAI nearly every day over this site. And since the vegetation is developing very fast, soil moisture is depleting very fast too. So in this kind of condition, actually we have a drought, but everything is green. So it's a bit contradictory if you like, but yeah. So after some stage, you don't have water anymore in the soil. LAI is very small. And in orange here, you can see the CO2 fluxes, the net CO2 flux at noon. So at noon, normally you have photosynthesis, and so you uptake CO2 from the atmosphere. This is why you have a negative value here. But when vegetation is very poorly developed during the drought, this flux is close to zero, except when you have rains. Because when you have rains, in warm conditions, it wakes up the bacteria of the soil, and you have a CO2 pulse related to soil respiration. So this is just to say that CO2 pulses can be triggered by rains after a dry condition. So this kind of behavior is usually observed in arid areas, but this year in Toulouse, yeah, it was like being in an arid area. So how to monitor terrestrial surfaces? So as I said before, we have models. We can be continuous at a global scale, but the problem of models is that some processes are too complex to represent. We also have in-situ observations, but they are very limited especially. And finally, we have satellite observations, but also with satellite observations, we can have gaps in the observations, and we cannot observe everything. So the idea is to try to take the best of these three worlds in order to kind of monitor the environment. So in Europe, we have several agencies like the European Space Agency, EUMETSAT for meteorology, and we have, so this figure shows that the space program in Europe is very rich. So ESA develops the Earth Explorer program with kind of research missions. EUMETSAT, of course, deals with METOP and Meteosat, as I said. And the European Union has been developing the Copernicus program, which is an operational program with a space component with all these satellites called Sentinels, and also a service component. And so there is connections, of course, between the three. And for example, Meteosat third generation, the sounder of MTG is hosting Sentinel-4, and METOP second generation is hosting Sentinel-5. So at Météo France, in terms of land surface modeling, we developed the ISBA land surface model, interactions between soil, biosphere, atmosphere. And so this model is included in the SURFX modeling platform, which is mainly developed by Météo France, but which is shared by many meteorological services in Europe, North Africa, as you can see here. So we have several versions of ISBA with several options, from very simple old options, if you like, to more sophisticated versions. So the most sophisticated versions are able to represent diffusion of water and heat within the soil, also able to simulate photosynthesis and CO2 fluxes, interactive LAI, and carbon storage. And in hydrology, we can also simulate the river discharge, for example, and same for snow. So in this presentation, what I will present is has been made using the so-called ISBA-NIT option, which includes a photosynthesis-driven phenology. So in this version, we are able to simulate LAI. Yeah. So when I say photosynthesis-driven phenology, it means that it is very simple with a very limited number of parameters. And this is very different from what is done usually with growing degree days and many parameters. And the advantage of using this method is that the leaf index we simulate is very flexible. So given that the LAI is very flexible, we can easily update the simulated LAI using observations, and we can assimilate LAI observations. So this is an example of what can be simulated. So still, the same period from 2001 to 2004. So the figure on the top is for grass. So I said that we have a very limited number of parameters. Actually, we have a minimum LAI value, 0.3, for example. Yeah, I think this 0.3 here. We have what we call a specific leaf area, which is a value to switch from leaf biomass to LAI, and we have a maximum leaf life expectancy. So we have 3 parameters. Also, as I said, LAI is very flexible. So, for example, we have an agriculture option in which we can simulate. So, in this case, it's irrigated maize. So we just constrain the model to its minimum value before an emergence date. And in this way, we can easily represent crops. So the ISBA model, it can be used in online simulations coupled with the atmosphere, but it can also be used for specific applications using an external atmospheric forcing, like IRA5 at a global scale, for example, AROM. So AROM is our high-resolution weather forecast model over France, or any atmospheric forcing. So this is an example of simulation of the ISBA model forced by AROM, atmospheric variables. And what you see here is surface soil moisture. So surface soil moisture is something that can be observed from space using microwave instruments. So here the green dots corresponds to Sentinel-1, which is a C-band SAR. And you can see, yes, this time series in 2017 and 2018 over a ground station over which we measure soil moisture close to Toulouse. So the observations, they are in red here, and the model simulations, they are in blue. So you can see that the model simulations, they are quite good actually. We are quite surprised to see that, because we use the AROM forcing without any correction whatsoever. So, and we were very surprised to see this very nice result. And actually our simulations look much better than what we can get from Sentinel-1. So in Surfex, in the end, there is 2 ways to integrate geographical information into the model. Of course, we can integrate land cover observation. So this is an example of the dominant land cover type over quarter degree grid cells over Europe. So this is the new version of our EcoClimate dataset. So EcoClimate second generation, in which we can integrate ESA CCI. So CCI is a climate change initiative land cover. So this is one way to include geographical information into the model. Another way is to use a land data assimilation system in which we assimilate LAI observation. So here on the top you can see LAI increments due to the assimilation, and over northeastern Spain here you can see these geographical patterns which correspond to irrigation. So yeah, just to show that geographical information is also contained in these LAI observations. So I already mentioned data assimilation. So the principle of data assimilation is to make the most of all source of information. So this figure is derived from a paper by Laos et al. For an atmospheric variable. So you have the model at a global scale, you have the satellite observations of this variable, which are bit space, but by combining the two, you can get an analysis which is closer to reality. So this is a general principle of data assimilation. And the idea is also to integrate observations when they are available, possibly in real time or in real time. So actually we can apply exactly the same technique to vegetation and to LAI. So this is what was implemented in Surfx. So we use a simplified extended Kalman filter, and this allows us to sequentially assimilate LAI observations. So we have a background forecast, if you like, as an initial condition. And then we integrate the observations to get an analysis, and the analysis is somewhere in between the observation and the initial value. So we need to have an observation operator. So in the case of LAI, it's very straightforward because we simulate LAI. So this is the identity. But if you want to assimilate something that the model is not able to simulate directly, you need to do something with this observation operator. So this diagram shows the way it works. So as I said, we can run Surfx offline. So we need an atmospheric forcing. We need all these variables here, which are usually produced by atmospheric models. And then we can integrate satellite observations into the model using this simplified extended Kalman filter data assimilation scheme. And when we do that, we analyze a number of control variables like leaf biomass. Actually, it's not really LAI, it's leaf biomass. And root zone soil moisture at several depths into the soil down to 1 meter. And improving these control variables, you also improve, in theory, the fluxes like evapotranspiration and photosynthesis, which is also called gross primary production. Yeah. So this is an example. So this is for year 2018. So maybe some of you remember that there has been a very severe heat wave in Northern Europe in 2018 during the summer. In this area, actually. So this figure on the left shows the RMSD of the simulated LAI without integrating any LAI observation. And on the right, you can see the reduction in RMSD after assimilating LAI observation. And so to do that, we use the H-rays ECMWF weather forecasts. And we try to look at what happens in terms of forecast. So this is for a lead time of 8 days. And you can see that even after 8 days, there is still an added value of the assimilation of LAI when you compare to the observations. So this also shows that LAI has a memory. And it is rather important to get good initial conditions of this quantity if you want to simulate land surface variables. So another example of that is for crops. So these red dots here in France corresponds to areas where there is a large concentration of straw cereal crops like wheat. And over these areas we have in situ observations of crop yields, of straw cereal yields, and we can compare these in situ observations to the simulated above ground biomass by the model. So on the left you can see what happens with the open loop, meaning without LAI assimilation, and there is a correlation of 0, which is not a surprise because ISBA is not a crop model. It's as simple as that. But after assimilating satellite observations of LAI, we get a very decent correlation. So now this is a key question is which LAI product to be used. This is an important question because the quality of the LAI products varies a lot. So in this figure, you have an example of time series over a forest. So the in situ observations consist of these dark dots here. And you have several LAI products. So you have in green, I think, yeah, the MODIS product here. And you can see that the MODIS product is very, very noisy. I would say that it is unusable. And then you have the Copernicus land monitoring service products. So the CLMS LAI actually is a family of products. They have several products from RT0 to RT6. So RT0 is a real-time product, if you like, very close to real-time. And RT6, so 6 means 6 periods of 10 days, so 2 months. And this is a consolidated product in purple here. So you can see that the product in purple is very, very close to the observations, and there is no saturation, because here we have LAI values between 5 and 6, which is a very high LAI, and many products, they saturate before. So, for example, the product here, Viga, which is disseminated by UMETSAT, it tends to saturate, you know, it does not get these very high values. Nevertheless, the UMETSAT product is rather smooth, contrary to the MODIS one. So be careful before using a LAI product. The quality is not the same for all the products. So another example of result. So this is the global photosynthesis. So you can see here on the left the trends in global photosynthesis with different approaches. So you can see that the absolute value of this quantity is very variable, and there is a high uncertainty on that. Nevertheless, if we look at the interlinear variability, we can see that when we assimilate LAI in ISBA, we get closer to the observed interlinear variability. Well, the observations, they are here in FluxCom, so it's not really an observation, but it's a data-driven estimate, if you like, at a global scale. Yeah, so this is another figure about global photosynthesis, showing that when we compare to FluxCom, we improve at a global scale both correlation and the unbiased RMSD. So in what I have presented so far, we assimilate LAI products, which is rather straightforward, as I said. But if we want to simulate new observations like SIF, I mentioned before, the fluorescence, or microwave brightness temperatures, or microwave backscattering coefficients, we need to do something because ISBA is not able to simulate these quantities. So to do that, we can use machine learning. So the idea is to use LAI observations to train a neural network. Of course, we can also use variables from the model, like surface soil moisture, in the training. And once we have trained this neural network, we are able to simulate microwave brightness temperatures, microwave backscatters, or solar-induced fluorescence. So once we have trained this neural network, we can kind of couple it with the model, and then the model will be able to assimilate this quantity to analyze leaf biomass and soil moisture. So this is something that was implemented in collaboration with ECMWF, who did that in their own system in the framework of the Corso European project. So this table shows results for several instruments. So we have tropomy, which is measuring SIF on Sentinel-5 precursor. I forgot to mention that SIF will be observed more and more in many instruments like Sentinel-5, but also microcarb and everything. So we also have here ASCAT, which is a C-band scatterometer, which is used over the ocean to estimate wind speed, but over land it's also sensitive to vegetation and soil moisture. SMAP, SMOS, which are L-band radiometers, and AMSA2. So in this case we use the X-band brightness temperatures. So what is interesting here is that there is this column which is a relative standard deviation. And you can see that with tropomy and AMSA2 we get relatively low values, meaning that we get more or less the same results throughout the world. So this is for global croplands. This is not the case for the other instruments like C-band or L-band, because it is probably due to the fact that at L-band and C-band we penetrate a lot into the soil vegetation system. This means that we are sensitive to soil properties which can vary a lot from one continent to another. So this is a map of RMSD for SIF at the top. So RMSD on the left, correlation on the right. So on the top you have SIF, the bottom you have X-band brightness temperatures, and you can see that these maps, they are very smooth for all global croplands. So this was for the training. So this is an example also for ASCAT over southwestern France. So what I presented before, we use a single neural network at a global scale. Here over southwestern France, we try to use a kind of more refined approach with one neural network per grid cell. So this is what we get in terms of RMSE for sigma knots in decibels. So it's quite good because the noise associated to the observations is about 0.3 decibel. So we are within this quantity. So this is the first training phase, and then once we have trained the neural network, we can assimilate ASCAT sigma knots, and this map shows the improvement we get in LAI after the assimilation of sigma knot. And actually we see, well, you don't know this region probably, but the largest improvements are for croplands around Toulouse. And in general, when we assimilate LAI or any observation of vegetation, the largest impact is over croplands, because as I said, ISBA is not a crop model, and there are many processes we don't represent. For example, we don't represent crop rotation. Around Toulouse, you always have something like 50% of bare soil, because there is a sequence between winter crops and summer crops, and they cannot be at the same place. So this means that you always have 50% of bare soil, and the model does not know that. So this is an extraction of leaf area index over this area where we have a lot of crops. So you can see a time series for 4 years. Again, well, it's not this, from 2015 to 2018. So in orange here, you can see the CLMS LAI observations. The model open loop is in blue. So as I said, it's much larger, twice larger than the observations, because the model does not represent crop rotation. In green, you have what we get when we assimilate the CLMS LAI. So we correct to a large extent the bias. We reduce the bias to a large extent, but not completely. When we assimilate SCAT sigma knots, we correct completely for this model shortcoming. This is due to the fact that with SCAT, we have no problem with clouds. We can see throughout clouds, and we have daily observations. And this is much more efficient to constrain the model than having one observation every 10 days. So this also means that, well, we need as many LAI observations as possible, or as many vegetation sensitive observations as possible. So this is an example related to the assimilation of troposif, which is a SIF product derived from Sentinel-5P. So this is again the same area, irrigated area in northeastern Spain, and you can see here again the main analysis increments in September 2021 when we assimilate the tropomi SIF, and yeah, you can see that the irrigated area is popping out very well. So here the spatial resolution is not very good. It's a quarter of a degree or tenth of a degree. Yeah, so this is irrigation. And this is what we get at a global scale. So at a global scale over croplands, yes, we improve the LAI simulation in general, except for some areas like Denmark. So don't ask me why, but we don't improve LAI there. So finally, so now I will be talking a little bit about fires. I would like to somewhat advertise this new European project, which is called Greeneo. So Greeneo is dealing on satellite-based services to support the European Green Deal. So there are several work packages, one for cities, one for agriculture, and one for forest fire danger monitoring. So I am co-leading this one, and INRAE, well, François Pimon is involved in this work package, and it's very interesting because in this work package we also have IPMA, which is the Portuguese Meteorological Services in charge of the land surface analysis application facility of EUMETSAT, and they produce FRP values from MTG. So in this work package, we already did a comparison of the FRP values with Institut observations and so on. So yeah, it's very interesting work package. So this is Greeneo. So this is a 4-year project. And another project, so yeah, so this illustrates what we want to do together with François. So again, we have this ISBA surface model in which we can integrate various data. And then the idea is to use kind of same technique of observation operator based on machine learning to produce new variables. So in this case, the objective is not to assimilate, but to produce new variables like LFMC. So the first results will be presented in the presentation by Jan Baer. So in this context, we develop what we call LDAS AROM automatic chain. So it's our land data simulation system, which is forced by the AROM weather forecast models. So we can get this kind of maps over France. Oops, sorry. So we get this kind of maps for forests. So this is for broadleaf forests. And this is a LAI analysis for the 9th of September 2024 on the left, and on the right you can see soil moisture at a depth of 1 meter. So we get it, this kind of stuff, automatically every day. So the system is uptaking LAI observations from CLMS and doing the simulations, everything automatically. And actually we do a forecast to catch up with real time. So in this case, remember I mentioned RT0, RT1, RT6. So RT6 is available, it's a very good product, but it's available only 2 months after the observation. And in this case we use RT1. Because RT0 we have a lot of missing data because of clouds and the quality is not very good. RT1 is already quite good. But RT1 is at least 10 days after the observation, so we use the forecast from R1 to catch up a little bit with real time. So this is a general idea. And from this, as I said, we can use machine learning to simulate new variables like LFMC. So we train from Institut observations from the French forestry system. But Jan will elaborate on that later on. Yes, and in the end we can get these figures that were presented by François already of LFMC maps. So this is for 2 contrasting years. So 2022 again, which was very, very dry, as I said, with many fires everywhere. And 2023 on the right. So another project, so this is a national project called IRICLIM, which will be starting in January 2026. So IRICLIM will be a component of a broader project called IRIMA. And IRIMA has a rather large budget of more than 50 million euro over 8 years. So IRICLIM is a 4-year project. We have 3 million euros. So I will be coordinating this project, and we will address several risks, if you like. So wildfires, of course, but also floods and geotechnical droughts. And also we will address vulnerability over France. So we will address what we call metropolitan France, which is continental France plus Corsica. So on the right you can see all the kind of disaster we can face. So well, tsunamis everywhere, everything. So in IRICLIM we will address droughts. So by geotechnical drought I mean, you know, these clay soils which can move during a drought and damage buildings. And in France it's becoming very costly because we have a lot of clay in France. This map shows the regions where there is a lot of clay and a lot of damages to houses when we have severe droughts. And this is now more costly than floods for insurance companies. So this is a very, very important topic, which is not completely different, by the way, from the wildfire, because both are related to droughts. So I believe that with the same tools we can monitor geotechnical droughts and wildfires, and also soil moisture can be useful, of course, to monitor floods. So this is a general idea, working together, getting ideas from all the communities to progress in the production of decision support services. Sorry. So in conclusion, I hope I convince you that LAI is important for many applications, and also for wildfires. I think that Jan will show that. Yeah, so when we assimilate LAI or LAI sensitive satellite observations, we can analyze leaf biomass and soil moisture profiles. So as I said, the Copernicus Land Monitoring Service LAI, which is now based on Sentinel-3, we consider that it is a good product, and this is what we assimilate. And we assimilate RT1 for near real-time applications. But as I said, there is only one observation every 10 days because of cloudiness, so they do kind of synthesis, if you like, of LAI every 10 days, and in some cases it's not enough to monitor vegetation that one. So this also means that we need to assimilate new observations in addition to the CLMS LAI. So in particular, in the GreenEO project I mentioned before, together with IPMA, we'll try to align, to test the possibility to align all the LAI products on CLMS, in particular the UMETSAT LAI products, and also to continue developing the assimilation of SIF and microwave data. Finally, there is many potential applications of this tool. So vegetation fire danger assessment, of course, but also clay shrinkage monitoring, hydrology and water resources, and maybe one day, why not, NWP. So yeah, so that's all for me. Thank you for your attention.
Thank you, Jean-Christophe.